linear activation function. The first one is the step function. Let me first talk about the step function, which is a linear activation function in the deep learning. So according to the definition that we have, step function is a linear activation function which is used for a regression problem. Its application is in hidden layers as well as in output layer of the convolutional neural network. As I told you that step function is a linear activation function. It is used for the regression problem. So step function gives us only two values, 0 or 1. Therefore, it is helpful for the regression problem. Its main application is in hidden layers as well as in output layer of the convolutional neural network. So I hope you got it now that what is step functions. We already know that what is a step function. Step function is a function which gives only two values, 0 and 1, which is helpful for the regression problem. What is regression problems? In the regression problems, we have only two values. We can use it in hidden layers and also in the output layer of a neural network. Since step function returns only two values, 0 or 1, as an output, therefore it is not helpful for multi-class classification problems. Vanishing gradient descent is also the main issue with step function. As I said, step function returns only two values, 0 or 1. It can be 0 or 1 as an output. Therefore, it is not helpful for multi-class classification problems. For example, if I need 5 in the output, or 6 in the output, or 7 in the output, step function doesn't help there because it only returns two values, 0 or 1. It cannot return 2, it cannot return 5, it cannot return 4. Therefore, it is not helpful for the multi-class classification problems. A problem where we need multiple classification, it doesn't help. And that's the reason it creates vanishing gradient. So vanishing gradient is the main issue with the step function because it restricted the output to 0 and 1. So that restrictions, that limited kind of output creates vanishing gradient descents in the model. I repeat it, how vanishing gradient descent creates. Because the output has been restricted only up to 0 and 1. There are only two possible values, 0 and 1. So it is not helpful for the multi-classification problems, and therefore it creates vanishing gradients in the model. So this is the main issue with the step function. I hope it is clear by now. Now let me show you the mathematical and graphical perspective of the step function. For example, if I have a piecewise function f of x equals to 0 when x is less than 0, 1 when x equals to and greater than 0. What is x? X is actually the summation of the input times the weight plus bias. So its expected output will be 0 and 1. So here is the graphical perspective where we have the output from 0 up to 1. Look, we know that in the step function we have only two possible values, 0 and 1. 0 when x is less than 0. Remember, when x is in negative form, what it means by x is less than 0, it means that if x is in a negative form, any kind of negative value will give us the output in the 0 form. So this is the main restriction here. Because of this restriction, it creates vanishing gradient descent problem in the model. But what if x equals to or greater than 0? If x equals to or greater than 0, its output will be 1. It will be only 1. Again, there is a restriction. It gives us only 1 if you go in the positive side up to infinity. No matter how big value you put there for the step function, it will make it up to 1. Its output will be only 1. And similarly on the negative side, whatever value you put here in the negative side, step function will restrict it up to the 0. If x is less than 0 means that if x is negative, the output will be only 0. And similarly, if x is greater than or equal to 0, in the positive side, greater than 1, 2, 3, 4, 5 up to infinity, or 0, it will be only 1. The output will be only 1. Remember, this is the 1. Now it doesn't mean that we have 1, 2, 3, 4, 5. It is not 5. This point means 1 only, 1. From here up to here we have only 1 point. These are the sub small points here. Look, this x is actually the summation of the input times the weight. We will see in the upcoming lecture that how we can take the product of the input with the weight, and then we took the summation. I'm going to show you later. So this x is actually the indication of this whole expression, which is the summation of the input times the weight. The output will be only 0 and 1. There will be only 0 and 1. These are the only two possible values for the activation function. If you see its graphical perspective, if I pass 5 as an input, it only returns 0 and 1. So we can say that it is not ideal for multi-class classification problems. Look, for example, this is a simple neural network with the activation function. Suppose the activation function is the step function. It is the step function. So whenever you pass 5 as an input, it only returns 0 and 1. These are the only two possible values in the output for this model when you use the step function, 0 or 1. So no matter whatever value you put it here, whether it is 5 or 6 or 7 or 8 or 9 or 10, whatever you want, ultimately the output will be only 0 and 1. And therefore we can say that it is not ideal for multi-class classification problems. If we have a problem where we need multi-classification, then it is not ideal for that specific problem, because it will restrict the output only up to 0 and 1, not more than this. No other value. So you will never get this 5 in the output. Now, rectified linear unit function, which is called a ReLU activation function. What is a ReLU activation function? According to the definition that we have, ReLU is a linear activation function which is used for regression problem. It is used in hidden layers as well as in output layer of the neural network. Look, ReLU stands for rectified linear unit. RE means rectified, L means linear, U means unit. Rectified linear unit activation function. It is actually a linear activation function which is used for regression problems. Remember, we have two types of problems, regression problems and classification problems. In the classification problems, we may have multiple classifications, but for the regressions, we have only two values, either 0 or 1, either positive 1 or negative 1. So this is the difference between regression and classification problem. ReLU activation functions is used for the regression problems. It is used in the hidden layer as well as in the output layer of the neural network. ReLU activation function blocks all the negative values and limits them to 0. Therefore, it pops off vanishing gradient descent, which creates problem in learning of the model. So it takes all the real numbers between 0 and positive infinity. ReLU activation function blocks all the negative values. If you put negative value as an input to the model, it will return only 0. Whatever value you put there in the negative form, you will only get 0 as an output. So there is a restrictions for the negative values, that you will get only 0 in the output. And that is the reason it creates a vanishing gradient descent problem. Vanishing gradient descent problem is a problem where it creates issue in learning of the model. The model cannot learn properly when vanishing gradient descent problem exists. So you have to avoid of vanishing gradient descent problem during learning of the model. It takes all the real numbers between 0 and positive infinity. So from 0 up to positive infinity, it takes all the real numbers. Now, according to the piecewise function, which is f of x equals to 0 when x is less than 0, x when x equals to or greater than 0. So here is the typical graph of the rectified linear unit activation function. It is a ReLU activation function. We already know that x equals to summation of the input times weight. Expected output will be from 0 up to positive infinity. Look, this is the mathematical touch of the ReLU activation function, where f of x is a piecewise function. According to this function, f of x, whether you put f of x or y, it is exactly one thing. Suppose if you put y, it is not an issue. So f of x equals to 0 when x is less than 0. F of x will be x when x equals to or greater than 0. which means that whatever value you put it here for the x, it will return the same, exactly the same value in the output if x equals to or greater than 0. As I said, x is actually the summation of the input times weight. So expected output will be from 0 up to positive infinity. Now when you look to the graph here, this is the typical graph for the ReLU activation function. For the negative values, it only returns 0. So it doesn't care whether you put -1, -2, -1 million, -1 billion, whatever you want. Whatever thing you put it here for the negative, ultimately you will get 0 as an output. But what if x equals to or greater than 0, equals to or greater than 0, which means on a positive sides, positive values. For example, if you pass 1 as an input, it will return 1. If you pass 2 as an input, it will return in the output. If you pass 1 million as an input, it will return 1 million in the output. So this x means that exactly the same value will be returned as an output if you pass that value as an input to the neural network. But don't forget, it will always return 0 if you put negative value as an input to the model. So the output range is from 0 up to positive infinity. Infinity is not included. Remember, infinity is not a number. From 0 up to positive infinity. 0 is included, infinity is not included. Let me show a simple neural network here. If you pass the input, you will get the output range from 0 up to positive infinity. Look, it is a simple neural network where we have used ReLU activation function. For example, what is this f? This f is the activation function. Look, x sub 1 and x sub 2 are the two inputs here. X sub 1 times w and then plus bias value. So in the output, it will return the value from 0 up to positive infinity. As I said, if you put any negative value, it can be -1, -2, -3, -4, up to negative infinity. Whatever negative value you put it here, -1 billion, whatever you want, as long as the input is in negative form, it will only return 0 as an output. But the time when you put positive value as an input, for example 1, it will return 1. If you put 2, it will return 2. If you put 10, it will return 10. If you put 1 billion, it will return 1 billion here. So from 0 up to positive infinity, it can return any number. Any number depends on the input. So whatever positive value you pass here as an input to this neural network model, it will return exactly the same value. I repeat it, exactly the same value. If you put 1, positive 1, it will return positive 1. If you put positive 5, it will return positive 5. But if you put it in the negative form like -1, -3, any number, any negative number will return only 0 in the output. So we can say that it is not ideal for multi-class classification problems. It is helpful for the regression problem, but not for the classification problems, especially multi-class classification problems, because there is a restriction. For example, in the multi-class classification problems, expected negative value in the output, which you won't get with the help of the ReLU activation function. You will always get 0 as an output for any negative value. Because of this restriction, it creates a vanishing gradient descent problem. What is vanishing gradient descent problem? It is a problem which creates issue in learning the model, in learning neural network model. It has issue during the learning. So you have to avoid vanishing gradient descent problem. Therefore, we can say that it is not ideal for multi-class classification problems, because there is clear restrictions that for negative values, it always returns 0. Leaky ReLU activation function. According to the definition that we have, leaky ReLU activation function is also a linear activation function. It is the modified version of the ReLU activation function. It is also used in hidden and output layers. Leaky ReLU takes all the real numbers between negative infinity and positive infinity. We know that ReLU means rectified linear unit activation function. So its modified version is leaky ReLU activation function. It is also a linear activation function, which is used in hidden layer and also in the output layer of the neural network model. So leaky ReLU takes all the real numbers between negative infinity and positive infinity. Why we call it leaky ReLU? as it is pretty clear from its name, leaky ReLU, which means that there is a slight leakage here in this activation function. If you compare it with the ReLU activation function, there wasn't any leakage. For all the negative values, there was 0 in the output. But in the leaky ReLU activation function, we have a slight leakage. We have a leakage here. So for negative values, it may return negative value as an output. This is the difference. Therefore, it takes all the real numbers between negative infinity and positive infinity. Leaky ReLU activation function doesn't block all the negative values. There is a slight leakage on negative side. Therefore, it has less vanishing gradient descent compared to ReLU. It takes all the real numbers between negative infinity and positive infinity. As I told you, it is pretty clear from its name, leaky ReLU activation function, which means that it doesn't block all the negative values, which was happening in the ReLU activation function. There is a slight leakage on the negative side. Remember, the leakage is only on the negative side. So there is a slight leakage on the negative side, therefore it has less vanishing gradient descent compared to ReLU. Because ReLU has a very clear restriction that for any negative values you will get only 0. But here in the leaky ReLU, we have a slight leakage on the negative side. So it takes all the real numbers between negative infinity and positive infinity. Let me give you the mathematical equation here where we have f of x equals to kx when x is less than 0 and x when x equals to or greater than 0. K is a small leak where x equals to summation of input times weight plus bias. Now let me show you the graph of the leaky ReLU activation function. This is the respective graph for the leaky ReLU activation function. Look, as I said, that on the negative side we have a slight leak. We have a slight leakage here. Now when you look to the graph, it's still trying to be linear. I mean, there is a small leak here on the negative side. So when you look to the equation f of x or y will be kx when x is less than 0. If the input that we pass to the neural network is negative, f of x will be kx. But what is k? That small leak is the k. So you have to put kx here. X is the input, but k is a small leak on the negative side, don't forget, not on positive side. But for the positive, it will be x when x equals to 0 or greater than 0, which means that positive values on the right hand side. 1, 2, 3, 4, 5, 6 up to positive infinity. When you compare the leaky ReLU activation functions with the ReLU activation function, this is the difference. ReLU activation function only returns 0 when x is less than 0 on the negative side. But for the leaky ReLU, it is kx when x is less than 0, where k is a small leak. We can clearly see here in the graph that there is a small leakage. There is a small leakage on the negative side, not on the positive side. On the positive side will be x if x equals to or greater than 0, which means that whatever value you put as an input to the neural network, it will return exactly the same value in the output. So we can say that the expected output can be between negative infinity and positive infinity. It is unlike ReLU activation functions. In the leaky ReLU activation functions, we still have negative values on the negative side. So if you pass a negative value as an input to the neural network model with the help of the leaky ReLU activation functions, you may get negative value as an output. But if you put positive value, you will get exactly the same positive value as an output. Look, these are the inputs that we pass to the neural network model. So if it is a positive value, it will return exactly the same value. But if it is negative, it may return negative value in the output with a small leakage, because we have a small leakage. Therefore, we put kx. So we can say that the expected output will be between negative infinity up to positive infinity. But don't forget, negative infinity and positive infinity are not included. These are not numbers. Infinity is not a number. Between negative infinity and positive infinity, it can be any number. If you plug in any negative values or any positive values, it will return that negative or positive values as an output. because of the small leakage on the negative side and also this linear graph on the positive side. Look at the graph for the linear side and also for the positive side. For the positive side, it is linear. If you take a slope here at 1, it has the same distance along x-axis and along y-axis. Similarly, at this point, we have the same distance along x-axis and y-axis because it is a linear graph. But when you look to the graph on the negative side, it is not linear. If you put 1 here, you may have some kind of negative value here along y-axis. If I take 4 along x-axis, you won't get the same 4 along y-axis because it is not linear. It is trying to be linear, but not linear. That's why whatever value you get along x-axis will be different along y-axis. But yes, one thing is for sure that you will get negative value as an output if you use leaky ReLU function in neural network. So from negative infinity up to positive infinity, it can be any number as an output. Now let me show you a simple neural network. This is a simple neural network where we have used leaky ReLU activation function. Here is my input. I want to pass the input here, and the output will be from negative infinity up to positive infinity. Look, as I said, that in leaky ReLU activation function, between negative infinity and positive infinity, you can put any number. It can be any number as an input, and it can give any number between negative infinity up to positive infinity as an output. For example, if you pass input as a negative value, you will get negative value at the end. And similarly, if you pass positive value as an input, you will get positive value as an output. So there is no restriction. There is a restriction. There is a slight restriction at the negative side, because remember, there is a slight leakage. The graph is not perfectly linear as we have at the right side, in the positive side. So at the negative side, still there is a slight restriction, but not as we saw in the ReLU activation function, where the ReLU blocks all the negative values and restricted them to 0. That is not the case in leaky ReLU activation function. You can still get negative value as an output in leaky ReLU activation function because of the small leakage. So I can say that it is ideal for multi-class classification problems. To some extent, we can say that we can use it for multi-class classification problems where we have multiple classification, not ReLU activation function. So this is the difference. There's still vanishing gradient issue, but not too much what we had in ReLU activation function. So I hope the point is clear now.